Hello, this is the first video of a Linear Programming 2 series on the simplex method and integer programming for OCR Discrete Further Mathematics, and it introduces the simplex method. The simplex method gives us an algebraic way of solving linear programming problems. It can be applied with more than two variables, which is important for many real-world linear programming problems. And this method can also be easily programmed, so in the real world, linear programming solver software is used widely. It is an iterative method that seeks to maximize the objective function. To understand how the method works, we'll look first at a two-variable problem and make use of the ideas we've already seen when solving graphically. So let's recap on the graphical method with two variables. So here is a 2D linear programming problem with decision variables x and y. And if we were given a context of a question, they would be defined as the number of in certain items in the question. And then three constraints, which are written in this case as linear inequalities. We also have the objective function, which is either a maximize or a minimize, and in this case it's a maximize. It's important to note also the additional non-negativity constraints. When we graph this, we note that the lines shown in green, red and blue are these constraints, but with equalities or equations rather than inequalities. There were then two methods to solve this, either what we called the objective line or ruler method or the vertex method. And we would remember that we would find the optimal solution at the vertices of a feasible region. So the vertices being 0, 0, 0, 10, 10, 0, 8, 4, or 6, 6. And the profit at each of those could be seen to be equal to 0 at the origin, equal to 100 at 10, 0, to be 90 at 0, 10, to be 114 at the point 6, 6, and 116 at the point 8, 4, using this objective function. We would have found the points 6, 6 and 8, 4 by using simultaneous equations. In other words, where the lines given in these constraints intersected. The simplex method does pretty much the same thing, but in a very systematic way. So it starts at the origin and systematically moves around the vertices of a feasible region, either initially in the x direction or, depending on the pivot, in the y direction. We'll explain that further later. As it moves, it increases the objective function p as it goes, until it reaches the one of the optimal solution. So if it was initially to move in the x direction, it would move to this vertex here, and then it would move and check there, and then on to there, and then but stopping once it reaches this optimal solution. We still need to find the coordinates for the vertex by solving simultaneous linear equations, but the simplex method does this by manipulating rows in a table that represent these equations, so we don't have to do the simultaneous equations for ourselves, or separately. The table set up is the first thing that we would do within the simplex method, and sometimes it's called a tableau. Well, solving two-dimensional linear programming problems graphically is fairly straightforward, but when there are three variables, if we're thinking geometrically, this means we need to move to 3D space. So, for example, if we had, instead of a 2D graph, we have planes instead of lines, and the vertices are in effect corners defined by the three constraints. Let's look at this in a little bit more detail. So consider a typical constraint with three variables, x, y and z. Then this inequality, if we replace it with equality, we would have this, and when this is plotted, this is a plane. You will have come across this equation of a plane type in Pure Core Further Maths vector series. It would look like this. Noting that this is the Cartesian form for the equation of a plane, rather than the normal form. If we were to plot these further constraints, noting the non-negativity here, then we would have some sort of polyhedron shape, and this would give us the feasible region in the 3D space. Remembering that the vertices in the 3D feasible region will be found by the intersection points of those planes. And the simplex method moves from the origin around the vertices until an optimal solution is found. As before, how the initial direction is chosen will be considered in due course, but relates to the choice of pivot. We would compare this to the ruler method or objective line method. Let's just think that the objective function is now represented by a plane, and consider that plane moving through that 3D shape. Whilst it's possible to get an idea about linear programming then in the three variables, geometrically solving using a graphic method is not really practical. And it's also not possible to extend these ideas to problems in more than three variables unless you happen to be good at imagining hyperplanes. In fact, algebraic methods have been developed to solve linear programming problems more efficiently via this simplex method. And technology in the form of spreadsheets and LP solver software is widely used in practice to solve linear programming problems of all sizes. So the simplex method is what would be behind this programming of this technology. In the next video, we will introduce the idea of slack variables used within the simplex method.